Comparing two population-independent samples to the table given in table 14.2 provides sufficient evidence to indicate a shift in the probability distribution for drugs A and B. That is, that the probability distribution corresponding to drug A lies either to the right or to the left of the probability distribution corresponding to drug B. Tests at 0.05 level of significance. We have two populations. From these two populations, population 1 and population 2, we select sample, in this case 6 and 8, a small sample. Because we have a small sample and we don't know how the distribution of the population, we have to use non-parametric procedure. If this population were normally distributed, we can use t-distribution study in previous chapter 9. But here we don't know anything about the population. Then we collect also our data, that is the samples 1, and from samples 2 we collect this data, but we are not going to use this number. We are going to treat this data as on one sample. Then we are going to put all together, and we are going to rank all of them. Then when we rank, we are going to start for number 1, number 2, number 3, until in this case 7 plus 6 is 13. We have 13 numbers. We are going to test the hypothesis if all of this value, the median of all of these values are shifted. If the median of these two populations were like this, the median is located approximately, so these two distributions approximately have the same distribution. When we select sample from this population, when we rank all of these values, we cannot distinguish which value belong to one population from the other. But if we have two populations like this, and the median are located here, then it's obvious that when we select sample from this population and sample from this other population, and we rank this population, for sure all of these values will be located here at the beginning. On all of these values that we select here will be located here. Then we are going to use the sum of samples 1 and the sum of the samples 2 to determine if these two populations have different distribution. That is the big idea in this procedure. Okay, let's start. Okay, the claim in this case is a two-tail test. Why is a two-tail test? Because the problem is asking if we have enough evidence to reject that the probability distribution for drug A lies either to the right or to the left. We don't know exactly if to the left or to the right. If this distribution is to the left or is to the right. Then could be both sides. We don't know which one is bigger. But after that, we collect our sample. But we notice that actually those values are shifted to the right of all of this. But we need to verify that statistically that the mean of this population is to the right of this mean. The median, excuse me, not the mean, the median. First of all, we can work this problem in Excel. And I recommend you use Excel. Let's open this problem in Excel. In Excel, we have this situation. We have the data here, samples A, samples B, drug A, drug B, that is reaction time for each drug. If we want to consider all of these values as only one sample, let's copy all of these numbers, copy here, and let's copy all of these other values, Control copy, Control C, and Control V. Let's consider all of these values as only one sample, and let's rank all of these numbers. And we are going to work not with this value, we are going to work with the rank, the sum of rank. We expect that the sum of the rank for the samples 1 and the sum of the samples 2 must be between certain values. Let's run. I will recommend to use in formulas, statistical formula, this function that is very helpful. Rank using average. What is the meaning using average? If we have two values tied with the same rank, then this function will assign the average of these two ranks if we consider these two values consecutive and distinct. Okay, let's use this one, and we are going to obtain immediately. Let's find what is the rank of 1.96 inside this data when we use the average. If we find two ranks that are equal, then let's go to formula, statistical formula, and rank using average. Then here, in this place, we need to determine which value we need to assign the rank, this value. From which set of data? The data is located from this point to this point. And in order, it means 0 descending order and 1 ascending order. Let's select 1 ascending order. If we we order this 1.96 will be located in the position number 4. And let's copy this formula in all of these cells. To do that, we need to fix my data. My data is located from D2 to D14. But let's fix D2, only the row, because the column will be the same. We need to fix only the row. Then when we do that, we can copy this formula in all of these cells. And we have the rank for all of this. Then the rank for the first sample, the sum of the cell sample is the sum of all of this rank, not this value. Remember, in non-parametric, we don't work directly with this value. We work in most of the cases with the rank. Then that is the rank. That is the first position, the second position, and so on. If these two values, for example, the second and the third value, the second were equal, let's write here 1.71. 1.71. Let's see what happened. Can you see? The position second and the position third, because these two values are tied, this function assign the mean between 2 and 3. The mean between 2 and 3 is 2.5. If the fourth one, first, second, third, the fourth one also were 1.71, then the average between second, third, and fourth is 3. Then let's verify. Can you see? 3, 3, and 3. This function is very helpful to order and to assign the rank. But let's recover our values. Then let's copy all of these values here. Okay. After that, we need to sum all rank corresponding to the first sample. That is the sum here. Equal sum, open parenthesis, all value located from here to here. Here also the sum of the rank of the second sample. Rank, remember, no values, rank is 66. Because in this procedure, we have to select the sum of rank for the sample with the smaller sample size. In this case, the smaller sample size is this. Then we have to select this as our test statistic. Then we have to go to the table. But before we go to the table, I am going to explain what is the logic of this procedure. Let's copy this here. What is the logic of this procedure? You can observe here that if this value were different, very different, for example, the first population were located, all value were located below the minimum value of the population number 2. If all of these value were all of them below to all of this value, then here we have the sample between 1 to 6 only. Let's do that. If we, for example, 2.24, let's write here in 2.24, instead 2.24, let's write 1.60. 1.60 is smaller than any of these. And also 2.41, let's change, instead 2.41, let's write, for example, 1.73. Can you see? In my first sample, the rank of all value taken from my first sample will receive the first rank, 1, 2, 3, 4, 5, and 6. The sample taken from my second population will receive the rest. Then the sum of all of this value will be 21, and the sum of all of this value will be 70. I can change all of this value for value smaller than this, but all of them below this, or any value bigger here, and we will obtain always this number, always. For that reason, we need to go to the table. Obviously, if we have all of this value smaller, the minimum value that this sum will be is 21, because we will have 13 observations, 6 and 7. Every time that we have 6 and 7, 6 doesn't matter which value are these. This sum will be always the same. For that reason, we can use those tables. Then in those tables, we have this. We can rank my data in this way, and we obtain the sum, and my test statistic will be this one, because it's the sum of the smaller sample. Which table we have to use? Because this is a two-type table, and alpha is 0.05, N1 is 6, and N1 is 7. We need to select the table 0.05 to tell, alpha 0.05 to tell. Which one is this? We have alpha 0.05 to tell and alpha 0.10 to tell. Here we have 0.05 by only one tell. We have only two tables for this kind of problem. Then we have to select this one. This is the table. If we work with this table, then in first sample have 6 observations, my second sample 7 observations. Which one are my reference number, my critical values? For 6 and 7, my critical value are 28 and 56. Remember, this sum, the minimum value is 21. But if I got a value smaller than 28, actually all of this value will be below to this value. The maximum value, the sum of all of this value will be 70. But if I got a value bigger than 56, is because because in this section we have several values that are bigger than this, most values that are bigger than this. That is the logic of this procedure. Then in this case, in our procedure, we got 25 and 66. Then my test statistic, remember, was T1, this smaller sample, the sum for the smaller sample, and this sum was 25 because 25 fall in the rejection region because the rejection region is outside this interval. We reject the null, we have sufficient evidence. Remember this structure for conclusion. When we got a value in my rejection region, we have enough evidence to reject the null or support the alternative. But when we got a value close to my expectation in the center, for example here, if we got a value here, we have insufficient evidence to reject the null or to support the alternative. That is the structure. That is the work that you need to show. You need to write the null and the alternative hypothesis. What did you know? The null is the two populations of reaction time corresponding to drug A and drug B have the same probability distribution. We assume that they have the same mean and approximately the same distribution, the same median, no mean, median. And the alternative is the probability distribution for drug A is shifted to the right or to the left of the probability distribution for drug B. What is my test statistic? Since drug A has a fewer subject, is smaller, this sample, than drug B, the test statistic should be T1, the sum rank for the first sample. Then the rank sum of drug A reaction time. That is my test statistic. Then my reaction region must be found on the table. Then in the table, we need to go to the significant level 0.05 and N16 and N27. We found these two values, 28 and 56. Then because 25 was my test statistic for in this region, we have sufficient evidence to reject the null because fall in the rejection region. And that is my conclusion. Since T1, the rank of drug A reaction time, it is in the rejection region. Therefore, there is sufficient evidence to reject the null or to support the alternative.